Hello friends, from the previous lecture onwards, we have been considering different ways of testing the mechanical behavior of the materials. In the previous lecture, we considered the tensile testing of the materials. Now when you relate this tensile testing or the mechanical condition involved in the tensile testing, it was similar to the mechanical condition that we have considered or we have been considering during our theoretical study of the mechanical behavior of the material on the stress condition that we impose. So whenever we studied about, be it the components of stress or whenever we considered the migration of the dislocation, one general mechanical condition was a uniaxial tension or a triaxial tension. So the question might arise, if we built the theory first and then made a suitable testing machine, or we started with the testing or tensile testing of the materials and then built the theory around it. So this is a legitimate question to ask. Did the theory come first? Did we theoretically conceive the tensile testing of the material? We began considering the components of it, and then based on that we built the tensile testing machine, or did we do the tensile testing first and built the theory around it? Now it is easy for us to answer this question, or relatively easy for us to answer this question, because we have spent some time considering the historical progress in the testing of materials. So therefore, at least you might now be able to give a convincing answer. So which came first? Did we begin with the theory, or did we begin with the testing of materials? Now, when you consider tensile testing, given that all the theories of the mechanical behavior of the material stems from it, we were able to talk about several distinct points that rendered that largely portrayed the properties of the material. When we consider the tensile testing of the material, and when we consider the way these results of the tensile testing are being presented, and when you consider the different points, the characteristic points of these tensile testing results, they largely talked about the property of the materials, and this we refer to them as the mechanical property of the material. So generally, when someone wants to understand the mechanical behavior or the mechanical property of the material, the go-to test would be tensile testing. So therefore, when compared to all the other tests, the tensile testing stands apart. So we need to know the position of the tensile testing with respect to the other tests. So when we want to understand the mechanical property, when we want to understand the mechanical behavior of the material, the go-to test or the preferred test is the tensile testing one. Now, it doesn't. This particular testing is not confined to a material that exhibits plasticity. It is not confined to material that does not exhibit plasticity. It is not material dependent. But whenever you want to understand the mechanical behavior, if you want to understand the mechanical behavior, the conventional way of understanding is usually the tensile testing. Apart from it, the other testings, they have been evolved or they have been developed to address a specific problem. So what I mean by that is, as the application of the material increased, and as we began using a given material for different application, and in the different application, the material began to experience different forms of loading, and based on that, the testings also developed. So therefore, all the testings that we consider apart from the tensile testing are application specific. So let me repeat, the tensile testing, if you have a material you want to understand the mechanical behavior, you have to go for this tensile testing. So mechanical behavior in general is understood by the tensile testing of the material. Even though it is rather restricted, all we are doing is imposing a tensile load, or rather a stretchability. All we are doing is considering the stretchability of the material. But when you want to talk about a mechanical behavior, when you want to estimate the mechanical property of the material, you will start with the tensile testing. Now other testings that we have, given that you have already had a lab course on the testing of material, you might already be familiar with other testing methods. So all the other testing methods, they evolved as the applicability of the materials increased, as the application expanded and people were searching for definite material for a particular application, and in that application the material began to experience, or they began experiencing a load that was significantly different from that of tensile loading. Other testing measures were developed. So therefore, the tensile testing is for generalized mechanical behavior, and all the other testings are for specific application. Now, one such testing method is what we will be considering in this lecture. We will try to accommodate one more in this lecture possibly, but this lecture will principally be on one of the testing method that was developed for materials that are being used in some specific applications. So there are specific applications wherein a specific form of loading is experienced by the material, and in order to understand the response of a material to this specific form of loading, this particular testing was developed. So apart from tensile testing methods, all the other testings are specific to an application. They are geared towards an application. So one such testing method is the torsion testing. The loading condition that is involved with torsion is rather straightforward. What you are essentially doing is twisting the material, and that is the reason why the strain, which we will talk about in a few moments, the strain associated with the torsion testing is referred to as the angular twisting. So we have certain application, for instance axles, particularly in the automobile industries or automotive industries. You have components like axle, shafts and such. So axle, shaft and others, wherein the material that you use in that application experience a loading condition that is, or a load that is significantly different from the tensile loading or compressive loading, and therefore this particular testing was developed. And instead of this testing came into being, instead of considering a sample of the material, the whole component was tested, and the response of this component to the imposed condition was studied. And however, now we have moved away from that position, and now in most cases we are using the sample of the material that is used for this particular application. Despite this, we still have machines which test the overall component. Say for instance, this machine tests, instead of testing the material in which this axle is made up of or shaft is made up of, they are capable of testing the entire component. So the torsion testing involves, as far as the mechanical loading is concerned, it involves a twisting action. And when you consider the machine, again assuming that you have already taken up a course or a laboratory course on different testing of materials, and that is the reason why we are spending very few minutes of the time that we are spending for the mechanical testing methods are relatively small. The reason is because it is assumed that you have already taken a laboratory course. I will just introduce or talk about few theoretical points that are theoretical concepts that are associated with torsion testing. So when you consider, just to brush up what you would have seen in a laboratory course, the torsion testing machine, it comprises of two heads. One is the twisting head and other is the weight head. These two heads, that is the twisting and the weight head, are two different ends of the torsion testing machine that grips your sample. So twisting head and the weight head, they are the two different ends of the torsion testing machine that grips your sample. If you have a sample that is of a cylindrical nature, so this sample is gripped at the two ends, and in one end the sample is twisted, while other end it is held firmly. So in this end it is held firmly, and in this end the sample is twisted, and this end is referred to as the twisting end, and the other end is referred to as the weight end. So we have twisting head and the weight head. Now by this action we are now able to introduce a load that is characteristic of torsion testing. Now when we impose such a load, what essentially happens is the material begins to twist. Now the way of understanding, it is possible for us to understand the load that is being given. So there is something that we impose. Now we want to understand the strain that is associated with the material that is being tested. The way the strain is estimated is first by considering an horizontal element. Supposing you have a sample of this form. Now we began by considering an horizontal element, and along the longitudinal axis of the cylindrical sample, and in that we consider 2 points, one at the twisting head and other at the weight head. Now when we began imposing the twisting load, what essentially would happen is this particular point will begin to move with respect to this point. So when you began imposing the twisting load, the new position of this point will be here with respect to the point here, which is close to that of the weight head. Now the strain that is associated with this torsion or with this mechanical loading is estimated by considering this angle here, which is theta. So in torsion testing, what you have is a weight head and a twisting head. You began by imposing the mechanical load on the twisting head, which rotates your sample with respect to the weight head. And when this sample begins to rotate, the longitudinal element that you have and 2 points along the twisting head and the weight head, one of these 2 points, it begins to move. The strain that is associated with this twisting event is now estimated by the angle that it forms with respect to its original position, and this theta is what gives you the torsional strain, or it is what calculates the, or it helps us to understand the strain associated with torsion. And in more technical terms, it is referred to as the angular twist. So what you have is the twisting of your sample, to put it simply, and this twisting of the sample is calculated by considering a longitudinal element and having 2 points in that longitudinal element, one close to the torsion head and the other close to the weight head, and by considering the position of the point that is close to the twisting head and comparing it with its original position, we will be able to calculate an angular element, and this angular element is what we refer to as the angular twist, and that is proportional to that of the strain, or that helps us to understand the strain that is experienced by the material when you impose a loading condition. Now, the way the torsion test is being done is we begin by imposing a load at the twisting end. We are in a way holding one end of the sample and we are twisting the other end. This twisting action is referred to as the torsional moment. So you are holding one end of the sample and you are twisting it at the other end, and when you consider the way we tested the tensile we tested the sample in the tensile testing machine, you could recollect we are able to impose a definite amount of strain and you were able to calculate the stress associated with it. So that is what we discussed in the previous lecture. The controlled parameter, the parameter that we control, is the amount of strain that you give, and that is the reason why we were able to see or consider the influence of strain rate on the mechanical behavior of the material. Here what we are doing is we are imposing a torsional load, or we are imposing a torsion to the material, and this torsion is measured as the torsional moment. So the way we are handling this sample during torsion testing is by introducing a torsional moment. You are rotating the sample with respect to a fixed point, and this rotation, this act of rotation, is referred to as the torsional moment. Now, when you impose a torsional moment, you are rotating, this is an action, this is a torsional moment. When you are imposing this torsional moment, the material, it offers a resistance to this torsional moment. If you could recollect, our primary description for the stress, or one of the definition of the stress, was the resistance offered by the material to a mechanical or to an imposed mechanical condition. So therefore, you are, in case of torsion, what you are doing is you are essentially imposing a torsional moment. You are imposing a mechanical condition in the form of a torsional moment. So moment is like this, and you are imposing a rotational or twisting moment, and to that moment what essentially happens is the material is resisting this moment, or resisting the effect that is caused to the material because of this torsional moment. The material is resisting it, and this we refer to as the stress. Now if we represent the torsional moment as M L, this is the convention that we have, and there is a stress that is that the material offers to prevent any deformation, and this stress, if you consider the nature of the stress, this is not a tensile stress, this is not a normal stress, but rather this is a stress that is acting along the plane or along the cross section. If you consider the resistance that the material needs to offer to this torsional moment, it should not be along the perpendicular direction, because the load is not along this direction. The load is not along this direction. In this case, the load is a torsional load, the load is a torsional moment. So when you have a torsional, when you have a load of this form, the resistance will be in the opposite direction, meaning it will try to ensure or retain the original nature of the material. And since the load is along, or it can be treated as the load that is along the circumference of the sample, the resistance will also be along this particular plane or along this circumference. And therefore, it is not the normal component of the stress that is resisting your torsional moment, but it is the shear component of the stress. So therefore, you impose a torsional moment, and there is a component of stress, or there is a resistance that is offered by the material that in order to avoid any plastic deformation or any deformation with respect or in response to the imposed mechanical condition, and given the nature of the mechanical loading, since it is a torsional moment, the response or the resistance that is offered, it is not along the longitudinal axis, but it is along a specific plane, or it is along the plane, and therefore the stress or the resistance that is offered by the material to the torsional moment is not a normal stress, but rather a shear stress. So therefore, you impose a torsional moment and you have the stress that is offered by the, or resistance that is offered by the material, which can be treated as the shear stress given the nature of the mechanical load that is involved in the torsional testing. Now, if you consider the way this particular resistance varies when you impose a torsional load. So you have, let us consider the cross section of the cylinder that you have, and in that you are imposing a torsional load. The resistance that is offered by the material at the center of the sample is 0. The resistance that is offered by the material to the torsional moment ML at the center of the sample is 0. And as we increase the radius of our consideration, the resistance increases. So therefore, at the surface, the material should offer a huge amount of resistance, and as the radius decreases, the amount of resistance that should be offered by the material to the imposed mechanical condition, it decreases. So this is the nature by which the material offers resistance to the imposed torsional moment. So you impose a torsional moment. The material does not offer the same resistance everywhere. At the surface, the material is expected to offer a huge amount of resistance, and as you consider the other planes that is beneath the surface as the radius of our consideration. So this radius, this R is the radius of our consideration. Let the actual radius be A, and now R, it varies from 0 to A. So R is the radius of our consideration and A is the radius of our sample. So R varies from 0 to A, and when R equal to 0, the resistance at that point is equal to 0. And when R increases, the resistance offered by the material, it linearly increases. So given that our focus is largely on the torsion testing of the materials, I'm not getting into the derivation or the discussion on how it is linearly related. So you have to look elsewhere for that argument. But for the sake of the discussion, let us adapt this particular theoretical precepts. That is that when you increase your radius of consideration from the center of your sample, the resistance offered by the material to the imposed torsional moment, it linearly increases. So what we essentially have is this resistance is dependent on the radius that we have considered. It is entirely dependent on the radius we are considering with respect to the surface of the sample. At the surface, you have maximum resistance, and when you get into the layers that are beneath the surface, the resistance offered by the material, it decreases. So this is dependent on the radius of our consideration. Now, let us assume a setup wherein the torsional moment is exactly balanced by the stress that we have imposed. And now, since the stress that we have imposed is dependent on R, This is expressed in this manner, wherein you have the resistance that is imposed by the material and you have the variable on which this resistance varies, and you have to consider the overall cross section of the material. So what we have assumed is, so we have considered that the torsional moment of the material, the torsional moment that we impose on the material, it is counteracted by the stress that is or a resistance that is offered by the material. You impose a torsional moment during torsional testing, and it is counteracted by a resistance from the material, and this resistance, which we refer to as the stress, and particularly in this condition, given the nature of the loading, it is the shear stress. This shear stress is not, or the resistance is not constant all through the cross section of the material. It is 0 at the center of the cross section, and it increases linearly as the radius of our consideration increases. So therefore, when you consider a torsional moment that balances the resistance offered by the material, you express it in this manner. You have your torsional moment, you have your resistance expressed in terms of the shear stress, and since the shear stress is dependent in this condition on the radius of our consideration, we have this expression here. Now the variable here is r, so you can take the shear stress tau out, and now if you consider multiply and divide it by r, you can write this expression in this form, that is r square by dA. What you have essentially done is taken this term out, you have multiplied and divided it by the r square, or rather r. You have taken this term out and multiply and divided by r. Then you have this expression wherein the torsion that you impose, or the torsional moment that you impose, the mechanical load that you impose, is counterbalanced by a combination of the resistance and the dimension of the parameters. So the load that you impose is counteracted by a combination of the inherent behavior of the material, that is the inherent resistance. The material, inherently it renders a resistance that is represented by this shear stress here, it is the tau here. In addition to that, there is also the dimension of the material that is counteracting this torsional load that you are imposing. This term here that talks about the dimensional influence on the torsional load is referred to as the polar moment of inertia of area. So since this is largely dependent on the cross-sectional area, this you have to have this of area term to qualify the polar moment of inertia. So what you essentially have is the imposed mechanical condition is resisted by two factors. One is the implicit material behavior that is mentioned here is in the form of the stress, and the configuration of the material, or the shape of the material, or dimension of the material, that is quantified, or that is introduced by the polar moment of inertia. So when you introduce or represent this polar moment of inertia by a term, say L, now the expression turns into tau by the radius of the cross section and L here. And since the radius of a cross section is not a variable and it's a constant, you can replace the R by A and L. So ML, that is the torsional moment that you impose on the material, is resisted by two factors. One is the stress that is implicitly associated with the material, and the other factor is the dimensional factor, and that is introduced by the polar moment of inertia, and you have the radius term involved in it. So this is how we relate the load that you impose on the material to the resistance that is offered by it. So the load that you impose on the material is measured in the terms of the torsional moment, and you are relating it to the resistance that is offered by the material by introducing the term stress here. So the implicit resistance that is offered by the material, that is independent of the dimension, is related in this format, in this manner. Now when you want to have an expression for the stress that governs the torsion of the material, it is expressed in this manner. You can just have to rearrange it, and you have the torsional moment, your radius of the cylindrical sample that you have, and the polar moment of inertia. So in case of tensile testing, estimating the stress was rather straightforward. All you have to do is consider the load and take the ratio of it with respect to the area of cross section. However, in case of torsional loading, given that the resistance offered by the material varies with the radius of our consideration. If you consider the dead center of your specimen, that is a cylindrical specimen, and if you consider the center of it, the resistance offered by it is 0, and as you increase the radius of consideration, it proportionately or linearly it increases. So given such a condition, you need to have a specific expression to calculate the stress that is associated with the torsional loading. And this stress is estimated by including or by treating the torsional moment as the load that you impose on the material and relating it to the resistance offered by the material, and also augmenting the influence of the dimension of the material. So you have the polar moment of inertia that acts as the, or that relates the load that you impose to that of the resistance offered by the material, and this is related by the polar moment of inertia. And from this relation, you will be able to calculate the stress that is associated with the torsional testing. And this is expressed in this form, wherein you have the load or similar a term that is synonymous to load in the tensile testing, that is the torsional moment, and a term that is synonymous to the cross-sectional area, that is the polar moment of inertia. And of course, you have an additional term that includes the radius of the sample that you have considered. So by this consideration, by relating the torsional moment to that of the resistance offered by the material, you now have an expression to talk about the mechanical condition experienced by the material during torsional testing. So this mechanical condition that is independent of the dimension of the sample is expressed in this format. So during mechanical testing, to estimate the stress is not straightforward. You cannot just say P by A. The stress in case of torsional testing, the way to express it involves these different terms. One is the torsional moment, the other is the polar moment of inertia, and this is the load that you impose. This you can calculate from, or this lastly talks about the dimensions of the material and the consideration that you render, or this term here, the polar moment of inertia, it talks about the nature in which the resistance varies when you impose the torsional loading. That is, the resistance is 0 at the center and increases linearly as you increase the radius, and A is the radius, the overall radius of your sample. And this way you have a unique expression for, or to estimate the stress, particularly the shear stress, when you impose a torsional loading to a material. Now let us consider how the outcomes of the torsion testing is represented. So the outcomes of the torsion testing is expressed in this manner, wherein you have here in the place of the mechanical condition that you impose. Generally, you have a stress versus strain curve, and in case of the torsional loading or torsion testing, what you essentially have a similar representation, but in case of the mechanical condition that you impose, you have the torsional moment, that is ML, and here what you have is the theta, that is the angular twist. So if you could recollect, this angular twist is largely dependent on the movement of a point that is close to the twisting head after you have imposed the torsional moment. So you have a longitudinal element and you move that, or once you impose the longitudinal element, the straight longitudinal element, the position of the one end of the element shifts, and this shift in the position can be calculated by the theta, and that is what we refer to as the angular moment, and that is what determines or dictates the strain experienced by the material. So that is what we use to estimate the strain experienced by the material. So you have the equivalent of strain, that is the angular twist in the x-axis, the equivalent of the load that you impose, that is the torsional moment, in the y-axis. Now the stress or the curve that you have conventionally will be of this form. And now what you observe is similar to the tensile testing. You have a linear region, so you have an elastic region, and there is a deviation from this elastic region after a definite point. And since this deviation is not quite easy to detect, it depends on the sensitivity of the testing machine. We need to consider an offset, and based on the offset we are able to calculate the resistance, or we are able to calculate the torsional strength of the material. And now when you are able to have a definite value for this, when you calculate or identify a definite value for this, let us assume that to be ml prime, and from that value you will be able to calculate from this and using this relation, from this value and using this relation. What you have done is you have considered an offset line, and from that offset line you are considering the intersection of this offset line and the result that you get from the experiments, and you from this you calculate the value and refer to that as the ml prime, and from this, by substituting this ml prime here, you will be able to estimate the resistance offered by the material that is independent of the dimension, or the torsional strength of the material that is independent of its dimension. So this is a term that is similar to that of the yield strength that we have in the or during the tensile testing. So for that we need to use this expression. You find the ml prime by constructing an offset or by considering an offset, and from that ml prime you will be able to understand the stress beyond which you will be the material experiences a permanent or a plastic torsional deformation. So this, to estimate that, to estimate a strength that is similar to that of the yield strength, you need to employ this expression here, wherein you also have polar moment of inertia. Now it is also key to note that there is no necking event during the torsional testing, and therefore you don't see a peak anywhere. However, there is a maximum point beyond which the material fails. So if you could see here, what you essentially have is a linear region which represents the elastic deformation to the imposed torsion load, and beyond a definite point, that is ml prime, you have a plastic deformation. And since there is no necking, what you essentially have is a monotonically increasing curve, but the rate at which it increases is rather restricted. Now the point at which the material fails is the point wherein you have to apply maximum moment of torsion or torsional moment. So when you want the material to fail, you have to impose a maximum amount of torsional load or torsional moment. So this point is referred to as the modulus of rupture. So the modulus of rupture is nothing but the load, the maximum torsional load that you have to apply, the maximum it's not right for to call the torsional moment as load, because the unit of it is considerably different. So the way we define the modulus of rupture is the torsional moment or the maximum torsional moment that is that the material can withstand before it fails is what we refer to as the modulus of rupture. Of course, it is considerably different, or the way we describe the modulus of rupture is different from the modulus of elasticity, but here it is the maximum torsional moment a material can withstand before rupturing, and that is what we refer to as the modulus of rupture. And this is one of the characteristic property that we can measure when we are doing the torsional testing. So what we have essentially seen is the torsional testing, when we do it, the outcomes of it is represented by considering the torsional moment and also the angular twist. It has an elastic region similar to that of the tensile testing, and there is a plastic region which is characterized by the non-linearity between the load that we impose, that is the torsional moment, and the strain that we observe, that is the angular twist. So these are linear. ml and theta, when they are linear, we are within the elastic regime, and when they become non-linear, we are moving into the plastic regime. And in that, towards the end, the maximum torsional moment the material can experience without failing, we refer to that as the moment or modulus of rupture. So these are the different considerations that one have to render when talking about or when considering the torsional testing of the material. So how to calculate the stress that the material experiences, or what is the shear stress that is involved, needs to be considered in terms of or by involving the polar moment of inertia. And this is how the response of the material to this torsional testing, or the outcomes that you get from the torsional testing, can be represented. Now, when you consider the strain exhibited by the material, or when you want to talk about the deformation exhibited by the material during torsion, we saw that when you have a setup like this, when you have a sample like this, and this end here is associated with the twisting head, and this end here, it is associated with the weight head. Now essentially you are twisting the sample in this end. Now the way we quantify the strain exhibited by the material is through the angular twist. So what we are essentially doing is we are considering an longitudinal element and we are considering its new position. So supposing the load is being, or the torsional moment is being imposed in this direction, the new position of this longitudinal element will be here, and the angular twist is nothing but the theta here. So the angle that is subscribed when you consider the new position of the point that is close to the twisting head with respect to its original point and the original longitudinal element, the angle that is subscribed, it was help us to characterize or get a parameter that is similar to the strain that you see in the tensile testing. Now it is possible, now that we have a way to estimate this theta here. So what we do is we use a setup called as troptometer during the torsional test in order to estimate this particular angular twist. Now since that we are able to estimate using this troptometer the theta or the angular twist, it is possible for us to relate this angular twist to the strain that we observe or the strain that we theoretically discussed. So since the stress that is involved during the torsional testing is the shear stress, and the strain associated with it is the shear strain. So the strain that is associated with the torsion test is shear strain, as it is the shear stress that offers resistance to the torsional moment. Now this shear strain, which is nothing but, which can be estimated by considering this shift in the position of the point that is close to the testing head, and this can be expressed, or this can be using this theta here, this shift can be estimated by considering the tan of theta. So what we have essentially done is we have essentially calculated the shear strain gamma by considering the tan of theta. There is nothing new here. We have just considered the we know the expression for calculating or estimating the shear stress, or rather the shear strain. We have seen it in a simpler case and something like this, and in this case when the new position of the corners have moved from A to A dash, we saw the theta here is the angle subscribed by the new position of this point here with respect to its original position, and the shear strain can now in this case be expressed by tan theta. We are adopting the same concept to this consideration here, and now the shear strain during the torsional loading is tan theta. However, it is also possible for us to introduce a new angle here in order to quantify this moment. So you have a moment of the point from say A to A dash, and now we want to measure this moment here. For that we consider the center of the cross section of the sample, and we measure the angle A and A theta makes with respect to the center, and if we refer to that as phi, and generally this phi is much lower for a given torsional moment. We are considering one individual torsional moment, and for a given individual torsional moment, since this particular phi is small, this moment A dash is nothing but, you have the radius that is A, and you want to calculate A dash, and this A dash, it subscribes an angle phi with respect to the cross section. So theta is with respect to the surface of the sample, and phi is with respect to the cross section. You have your center of the cross section, and from that you calculate, or you want to estimate A dash. So now when you do that, the way you can calculate, or the way it is estimated, given that theta is phi is relatively small for a given torsional moment, so A dash is nothing but phi A. So essentially we have an expression for, or it is possible for us to relate the angular twist to the shear strain. So the shear strain is nothing but tan of the angular twist, and if you consider tan theta, it is nothing but the length of this longitudinal element, which is usually the length of the overall sample. So when you consider tan theta, it is nothing but A dash by the length of the longitudinal element, which is nothing but the length of the overall sample, and we need to have an expression for this A dash. So this A dash, if you consider the center of the cross section and you measure the angle subscribed by the points A and A dash. With respect to the center, you have phi, and since this phi is so small, you have an expression for A dash, and therefore the tan theta can be expressed as phi A by L. Again, since we have already introduced L as the polar modulus of inertia, maybe here we can use L bar. So what you essentially now have is you are able to relate the angular twist, that is a form of a strain that you observe during torsion testing, to that of the shear strain. So this you have done by considering the center of the cross section of the sample and calculating the area or the angle with respect to the center of the cross section when a point A moves to point A dash. So essentially you have now related the angular twist to the shear strain. So this is the expression for the shear strain when you consider the length and the radius of the cross section and also include the change in the position of the points of within the longitudinal element with respect to the center of the cross section. So using these parameters here, we have now essentially translated the angular moment to, or the angular twist to, the shear strain. So even though angular twist is a way of measuring the strain associated with torsion, we have now through this angular twist now able to calculate the actual shear strain that a material experiences during the torsion testing. Now with this we will wind up our discussion on torsion. I'll just like to say a few words on how this torsion test is used for other applications as well. Meaning, we saw that this particular torsion test is used in order to estimate the behavior of a component or the behavior of the material that is being used in a component wherein the material experiences a torsional load in an application. In addition to that, by increasing the temperature of torsional testing and by increasing the temperature and seeing how a material responds to the torsional load, the forgeability of the material is studied. In addition to offering an understanding on how a material in an application wherein the torsional load is predominantly employed, in addition to giving that understanding on how a material would respond to a given torsional loading, how a component in an application would respond to a given torsional loading, when you include the high temperature component to it, when you add an high temperature component, or when you increase the temperature in which this particular torsion testing is done, then what it essentially tells us is how well you can forge a material, because forging of a material involves different forms of loading, and if a material at high temperature is allowed it can withstand sufficient amount of torsion load, it means the material is exceedingly forgeable. So this understanding can be gained by doing high temperature torsion testing of the material. So in addition to rendering information or understanding on a specific application on how a specific material would behave under a torsion condition or under torsion loading, when you increase the testing or temperature of the testing, it is also possible for us to understand the behavior of the material for a definite processing condition. Forgeability is not an application, or it is not based on an application, or it is not for an application. It is for a processing condition, and this processing condition is nothing but the forging of the material. And when your material is able to withstand sufficient amount of torsional moment at high temperature, it means your material is highly forgeable. If not, the forgeability is not there for this given material. So in order to understand the processing technique that can be used for a given material, the high temperature torsion plays a role. So in addition to an application, in addition to considering or estimating the suitability of a material for a given application, torsion testing when conducted at high temperature will help us understand the forgeability or the the way we can process. It gives an idea on the way we can process this particular material, particularly by in terms of the forgeability of the material. And now, once you talk about the high temperature and high temperature testing of the material, of course, similar can be, we saw that there is an influence of temperature in the tensile testing, and using the temperature, you can also, at high temperature, you can also conduct the torsion testing, and this torsion testing helps us understand the forgeability of the material. And now, there are tests being done wherein the high temperature is the necessary condition for this test. So, you have materials that are operating at high temperature. We have materials that are operating at temperatures that are close to its melting point rather than its room temperature or rather than the ambient temperature. So such materials we refer to as the high temperature materials, and we want to understand the behavior of the material during its application. So we have a material that is operating close to its melting point when you consider its closeness to the ambient temperature, and we want to understand the behavior of the material, the mechanical behavior of the material at this temperature at which it is operating. So the operation of this high temperature material, it depends on the temperature at which it's operating, and we want to understand the behavior of the material at that high temperature. So for that, the test we do is referred to as the creep tests. Now, we saw in tensile testing, there is a possibility of understanding the influence of temperature. So in order to understand the influence of temperature, you change the temperature at which you test your material. So this is one additional feature of the tensile testing. It is not exclusively meant for it, but we need to see or understand with respect to temperature how the properties or the behavior varies, so we increase the temperature. And similarly, in case of torsion testing, what we want to understand is the forgeability of the material, or we want to see which processing technique will be suitable for this material, and therefore we increase the temperature and do the torsion testing. So all these, in both tension and in also torsion, the high temperature is an additional feature. However, there are tests wherein the high temperature is the undergirding phenomenon, high temperature is the characterizing feature. So in other tests it's the additional feature, and in this test is the characterizing feature, and these tests are referred to as the in these tests wherein the high temperature is generally the necessary feature or the characteristic feature, these are referred to as the creep test. Even though we have the creep test being characterized by the high temperature. So whenever we want to understand the high temperature behavior of the material, again the temperature here, the high temperature is not a definite value. The high temperature here is with respect to the melting point of the material, and when you have a material operating, say for instance, if this is your ambient temperature, say A, and this is your B, that is the melting point of the material, and your material is operating in this region O, which is close to the melting point when compared to the ambient temperature, then what you essentially have is the material operating at high temperature. Now, when you want to study the high temperature behavior of the material, even though we go for the creep test, creep doesn't mean high temperature behavior of the material. So it is important for you to understand, even though creep test is carried to understand the high temperature behavior of the material, creep doesn't mean the high temperature behavior of the material. Creep means time dependent behavior of the material. So even though creep test is used to understand the high temperature behavior, creep doesn't mean high temperature behavior. Creep means time dependent behavior of the material. So in this next lecture, in the upcoming lecture, we will see how this time dependent behavior of the material plays a critical role when we consider high temperature, or why time dependent behavior of the material is usually studied when considering the high temperature behavior. So from that we will begin our next lecture on this particular testing of materials. So goodbye.